So you'll have noticed that we spend a lot of time talking about energies, particularly energies of electrons in molecules. The entire first part of this course was talking about how the electrons in atoms go lower because they make molecular or extended structures. So we have the obsession of energies of electrons, and so our understanding of chemical reactions, we shouldn't be surprised if we're still obsessing with the energies of electrons in bonds and otherwise. We have to talk a little bit more about other kinds of energy too. We already did. Remember, we talked about kinetic energy of gases. We remembered about RT. We talked about thermal energy, how we can estimate thermal energy in terms of the gas constant, R times temperature. So we've already heard of another kind of energy. So now we have these two kinds. We have like thermal energy, and we have the energies of electrons in bonds and stuff. So to understand chemical reactions, we're going to have to figure out what the role of both of these is and how energy is balanced between those. And this really is in the realm of something called thermochemistry, where thermochemistry tells us about heat and energy in reactions, and more generally thermodynamics, which tells us about heat, energy, and chemical processes in general. So thermochemistry and thermodynamics are really important because they allow us to do quite clever things. In other words, they give us tools for figuring out how to understand reactions, even reactions we can't actually do. And so here's an example of one. So if you take carbon, solid carbon, and we know that's almost certainly in the form of graphite, and let's imagine you want to combine graphite with oxygen to make carbon monoxide. Well, that's a chemical reaction, obviously. The definition of a chemical reaction is we make new chemicals which have new bonds, and so we have a carbon-oxygen bond. That's obviously a new reaction. So this counts as a burning or a combustion because it's a reaction with oxygen. So if you try and do this, and you might want to imagine, oh, I want to know everything about this reaction, you can't do it. The reason you can't do it is you're definitely going to get some carbon dioxide gas formed as well. And so, but thermodynamics allows you to figure out how to examine the energy flow in that reaction all on its own. So to get there, we need to talk about different kinds of energy. Thermodynamics is concerned particularly in energy in the form of heat and work. We're going to describe what those are. And so, yeah, let's talk about energies in molecules. And so we already introduced this a little bit. We remember with temperature, we decided temperature gives us an indication of kinetic energy in molecular systems. And remember that kinetic theory of gases, and we decided it even helps us, we can use that for systems which aren't even gases too. Temperature doesn't really measure energy in the sense that temperature is what's called an intensive property. And we don't introduce these terms to confuse you with terms, but some terms we need, right? So it's an intensive property. What that means is it doesn't depend upon how much material you actually have. Contrast that with something like volume and mass, which clearly depend upon how much material you actually have. And so these are called extensive properties. And again, those words aren't important, but understanding the difference between the two is. So let's sort of give an example of that. Imagine we have two blocks of iron. One's like 1 millimeter cube, that would be small, right? And we have another one which is 5 centimeters cube, that would be very large, right? The size of a hand. And imagine both of these are at 60 degrees C. The larger block, would feel a lot hotter, right? A lot hotter, even though the temperatures are identical, because there's simply, there's more energy contained in the larger block, right? So in that sense, temperature isn't enough, right? If we want to understand energy, just knowing the temperature is not enough. We have to have some measure of energy which is in terms of the quantity of material that we have. Or, that means the number of molecules or the number of moles. So a convenient quantity we're going to be using is in terms of moles, right? We already decided the moles are easier to deal with than molecules. So we use something like kilojoules per mole, energy per mole. So different kinds of energy. So kinetic energy we talked about. Now we know that temperature is not enough. Kinetic energy is important, and potential and internal energies. So energy, right? So kinetic energy, that's something that a molecule might have. Let's imagine we have methane. This molecule is called methane, and methane is a gas at room temperature because at room temperature, RT is sufficiently large to overcome the intermolecular forces, so it becomes a gas. So this is methane, and methane has a molecular formula of CH4. So methane, we have these methane gas molecules, and they're flying around, right, in random, chaotic, rapid motion. They're colliding with the walls of the container, they're colliding with each other, and so that energy that they have as a result of motion is called K. We already talked about this, K, and that's the kinetic energy. It's not the only place where energy can be inside a molecule too. However, there's also what we're going to call potential energy. And the potential energy is in the bonds. Remember when we talked about making bonds, we said the reason that two atoms are going to make a bond is because in doing so, the energy electrons are going to go down. Well, when the energy goes down, it doesn't disappear. There's still energy there. And so the potential energy is the energy which is contained in the bonds. The electrons in bonds still have energy. They don't have as much energy as they had when they were not in a bond, but they still have energy. That's a different kind of energy, and so that's P. So these two kinds of energies, this is where energy can go into a chemical system, either in kinetic energy as the molecules move around, or it can be stored in potential energy in the bonds. And we can get sort of more subtle about exactly the different places kinetic energy can go, exactly where the potential energy go, but this understanding is enough. And that actually allows us to define a rather new important quantity, something called the internal energy. And the internal energy is simply both of those things. It's all the places where energy can go. And so the internal energy is simply P, the potential energy, plus K. So the internal energy is simply all the places where energy can be inside a chemical system. Mainly it's in the bonds, and mainly the kinetic energy. There's some other small things too, but if we understand that, we understand basically this is the internal energy in a chemical system. This is the internal energy, that's the thing that's going to change when something undergoes a chemical reaction or some other kind of process too. So this is our starting point for understanding how energy changes when we do a chemical reaction.